relation to total maps. But the elements function, what does the elements function do? It glues all of those keys together, ignoring comparisons. This abstraction relation is not tuned to the elements function. And remember how long that proof was that I showed you of the elements relate theorem. I showed you a whole page of proof with an admitted at the bottom for you to fill in. So let's examine this abstraction function a little more. Let's take our bogus tree with 3 in the left child of 2, and let's relate it to its abstraction. Well, what's its abstraction? Has only the 2 in it. It's thrown away the 3. And you can step through this proof yourself to see that the combined function says here x less than 2 and 3 equals x. And we can throw away this case where we would have to prove that v3 equals default, which isn't true. So this is just an example of how the abstraction relation works like the lookup function. Okay, we're not done yet. What we want to think about this theorem, can relate. If T is a well-formed search tree, then it should abstract to something. What if we made an abstraction relation that was always false? I can prove the following theorem. If a tree abstracts to a content and we look something up in that tree, we get the right value. Right? So what we really require is that if T is a well-formed search tree, then it means something. That there exists a total map such that the abstraction relation abstracts it to that total map. I call this can relate. It's an essential thing you must prove about your implementation of an abstract data type. This is pretty easy to prove. It's part of the exercise. It should take you just a couple of minutes. Now, with this particular abstraction relation that we defined in this file, we can even prove something stronger. Even if it's not a well-formed search tree, it relates to some value, to some total map. We shouldn't expect to be able to prove this kind of thing in general, right? It happens to be provable here. It's easy to prove. You could work on this one first and then prove this one as a corollary, obviously. I call it unrealistically strong can relate because in general you shouldn't expect this about your abstraction relation. Okay. Here's an alternate abstraction relation that take the tree, give me the list of pairs, key and value, convert that to a total map with list to map. That's my abstract value. So call that abs x. Remember, when you're proving that an implementation satisfies the requirements of an abstract type, you can choose whatever abstraction relation you like that allows you to prove all of the theorems about the interface functions. So this is a perfectly good abstraction relation, and you can prove, that the interface functions behave correctly. So here's an example. We're going to prove elements relate x, which is that using this alternate abstraction relation, the elements function behaves properly. So what we need to prove, remember, about elements relate is that list to map of elements T equals CTS. And let's do H and F in H0, which says that. So that's easy. Why was this proof so easy? Well, here we have an abstraction relation that's tuned to the elements function. What's going to happen when we use this abstraction relation to prove the properties of lookup? It will not be so pleasant. Okay? So we could start with this. If T satisfies that abstraction relation to some total map, and we look up T in K, then we get the total map on K. This is not true. Let's prove its negation instead. So it is not the case that if T relates to a total map by abs X and we look up K in T, we get the same thing as we look up K in contents. How are we going to prove this? Well, we'll use the bogus tree. So here's our bogus tree. You can see it's used in the proof. Somehow the left side is going to disagree with the right side. That's fine. So here's the theorem we should prove. If T is a well-formed search tree and it relates to contents by the alternate abstraction relation, then the lookup gives us the right value. All right. Well, here we have the elements function. Remember that the elements function was not friendly to induction. Right? If we just do induction over the tree, it doesn't follow the inductive structure of that elements prime, which was optimized for efficiency. So we're going to rewrite by the theorem that slow elements is the same as elements. And now we have slow elements, and we can do the induction. Look, don't do this homework exercise. It's optional, right? When you prove the correctness of an abstract data type, you only need to do it one way, not two ways. Abs seems to be fine. All right, it just illustrates that we had choices. Okay, so now let's take this set of theorems about the interface operations of binary search trees and organize them into a formal abstract data type. So the way you can do this in Coq is with a module and a module type. Module type, here I have the module type table, specifies the interface of a module. So what does this module type say? There is a parameter v that's a type, so the type of values. There's a default value, which is a v, right? These are parameters. If you use the word parameter or axiom outside of a module type, you're adding new axioms to the logic. And this could make things inconsistent and enable you to prove false, which is all too convenient. But inside a module type, you're just adding things that will have to be instantiated in the implementation of the module. So this is not dangerous. There's some parameter table that is the implementation type, right? We will instantiate this one maybe with trees. We have a definition, key : nat. The module has to provide a value for the empty table. The module has to provide a get function whose type is key : table : v, and a set function whose type is key : v : table : table. Then, so far we can do all of this in ML with modules, or in Java with interfaces, right? But here's the part we can't do in ML or Java, which is state theorems about the behavior of the operators that the operators are actually guaranteed to respect. So the important theorems for tables, well, if we look up a key in the empty table, we get the default value. So get, set, same, or the get empty, get from empty. GSS, get, set, same, says if we update, if we set k to bind to v in tree T, and in that tree we get k, we get back v. And finally, get set other for j not equal to k. if we set at k and get at j, we get the same thing we would have gotten in the original tree. So this is the proof theory of finite maps with update, or maps with update in general. Okay, so we need to just provide an implementation of this table and recall our total map type, which is nat arrow v. Total maps can provide an implementation of this abstract interface. So here's our module, maps table, which respects the interface table. It has definition v : equal type. That will satisfy the parameter v type in the module type. Has a default value, has a table type that's just total map on v. It has an empty table that's just t underscore empty on the default value. It has a get function. Get km is just apply m to k. You've seen this before. Set kvm is just t update mkv. The get from empty theorem we have to prove. So here's our proof. Reflexivity, that was easy. Get set same, we have to prove. So let's unfold get and set, and this looks like our friend t underscore update. So that's easy. And get set other, if we unfold, that's just t update neek from the total maps library. Okay, so it was very easy. Now when we say end maps table, Coq will check that every interface specification in the module type was actually provided in the module implementation. Great. Now we can do it for search trees. So tree table is another implementation, another module that satisfies the module type table. For table, we'll use tree of v. For key, we'll use nat. For empty table, we use the empty tree. For the get function, we will use the lookup function. For set, we will use insert. For gempty, we just prove it by reflexivity. But GSS, if we unfold get and set, now we have to prove this theorem about lookup and insert. Now, you could prove this by induction, but I claim we've already proved the things we need. No, we haven't. You're going to prove this afternoon in the homework the things we need, and they are these theorems. First of all, we have this theorem, unrealistically strong can relate, which says for any tree, there exists a total map that is the abstraction of that tree. All right, so let's do that with tree T. So we destruct unrealistically strong can relate, and we get CTS, the total map, that is the abstraction of T above the line at H there. Now, remember the function insert relate. If we use insert relate, we get this fact that insert kvt abstracts to t update contents kv. And then let's look at lookup relate. So that says that if we look up k in insert kvt, well, because of this abstraction, we'll get the same thing as t update contents kv at k. All right, now let's rewrite by h1 down here. And we get this proof obligation, which is about t update. And we have a theorem for that. So the point is, having proved the appropriate things about the abstraction relation, that your binary search tree relates to the abstract total map, then you can prove all the interactions between the operators just using the theorems about the interactions between the total map operators. like this function right here. And so in the homework, when you prove this GSO theorem, it won't be any longer than this, really. You'll use the properties of the abstraction relation and the properties of total maps to prove it without any induction at all. Okay. But we used can relate. No, what did we use? We used unrealistically strong can relate. So isn't that cheating? Right? We shouldn't expect this in general. So yes, we can make a binary search tree module right here quite easily. But when you do this next month with some other data structure, and you only have a can relate function that requires this extra invariant property, the representation invariant, how are we going to do this? Because we represented table as tree, that's the data structure. Some of those trees are well formed and some are not. And if we get a ill-formed tree, then it may not satisfy these theorems, like in this case GSS and GSO. So we need an implementation of the module type where we only have well-formed trees. How do you do that in what?
Subset type?
Yeah. So in Java or ML, you enforce that you only have well-formed trees by, not letting anyone else forge them. But we want to describe semantically what's happening in the logic. And so for that, we will use dependent types in a certain way. So let's look at exist. In fact, let me print exist. There's an inductive type in the Coq standard library, SIG, with one constructor called exist. And what it builds is this type, which is basically a SIG type. If we turned off notation, you could see more clearly what this is. I don't have time to turn off notation. So this is a value in this type is an x of type A along with a proof of P of x. So it's an x that satisfies the predicate P. Not just satisfies it, but satisfies it constructively. It gives you the proof. Okay. Now to build a member of this SIG type, you have to provide x, and you have to provide a proof of P of x. Okay? And to do that, you apply the exist constructor to x and P of x. And then there's this useful function, project one from a SIG. It projects from this thing the value x. You can get the actual value of type A. So this gives you the x, throws away the proof. Like any projection on tuples, throws away all the elements except the ones you asked for. And proj2 of a SIG gives you the second component. So given E, which has x and a proof of P of x, it gives you a proof of P of x. Right? So we're going to use exist to build them, proj1 sig to get the value, proj2 sig to get the proof of the property. And now it's very simple. The table type will be the type of trees x such that x satisfies the search tree property. Okay. Now, here's where we have to prove well, hold on. Let me not skip a step here. The get function, we're going to do our binary search tree lookup, but we can't do it directly on M, which is a SIG. We have to do it on the tree that's buried in there. So here we applied proj1 sig to M. So the computable operations get and set, get just uses the value and ignores the proof. But what does set do? Set has to build a new tree. So